when the phonons coming down, it is losing the vibration around the surroundings. And when you vibrate something at very high vibrational frequency, that is nothing but at high temperature. And that is how create the heat energy. Because heat energy can be described as a vibration of the molecule at higher frequency. So that is how, if you remember, I was talking about that when you're talking about the microwave interaction, that when you heat something in the microwave, why it heats up? Because it gets the energy from microwave go to the excited state. When it's losing the energy, it is actually creating a vibration all around your food. In the lower level of the lattices or the solid structure of the food, it is creating vibration of the phonons. And when the phonons are actually trying to come down, it is actually releasing as a heat. So that the full heat is actually heating up. Similar thing happens over there when I am actually stopping my nucleus and still hitting it with a strong gamma ray energy, but I'm not letting it move. So it is actually creating vibration, this lattice vibration. And it can lose energy as heat energy. Now, over there, what is the recoil energy ends up to? The recoil energy is not nothing but some bunch of phonons. And what is the minimum phonon you can get over here? What is the minimum value of N is possible? Again, going back to the next slide, I'm just writing the same equation one more time. It is the ER is equal to E translation plus E vibrational. E translation is 0. E vibration is a summation of I equal to N H cross omega I at different frequency, and N can be any integer starting from 0. So what is the minimum value of N possible? Is 0. So what is the minimum value of rotational, the recoil energy possible? It will be 0 when N is equal to 0. And what will be that condition will be known as recoilless or recoil-free condition. And if I'm able to do my system in such a way, so there is quantum mechanically possible some state N equal to will be 0. And at that condition, what will happen to my energy absorbance system? At that condition, what will happen? My absorbance energy and my source energy will have a lot of common area. That means a resonance condition. That means I'm going to get a signal coming from the source to the absorber. Previously, they're way too far because of the recoil energy. Now they are close enough and we can have a lot of space where they actually have the same energy at the same position. So they can resonate the energy pretty well. And I will have a very nice energy transition from a source to the absorber. That means using a source of nuclear transition, I can excite another nucleus of the same transition. And that is the same thing that Boy did in the 1950s. And what he invented, a recoilless condition or recoil-free condition for doing the transition of the nucleus or nuclear transition. And any guess what is the name of that boy? The name of the boy is Rudolf Mossbauer. And according to his name, this particular phenomena is known as Mossbauer effect, where you can have some condition where you will have recoilless transition. And very interesting fact, he was doing this work and finished this work in 1957 as a part of his thesis research. And in 1961, he got the Nobel Prize for it. So there was time that you can finish up your thesis pretty well and get the Nobel in 4 years. Now you have to wait to do very well up till at least 40 years and get a lifetime achievement award, which is the Nobel Prize nowadays. So days were different. Anyways, so coming back to here, we'll stop over here today, where I hope I am able to convince you few important things. What are the take-home messages? So I'll go back a little bit. So the first important factor is that nuclear spin state change and nuclear state change are two different phenomena. Nuclear spin state change requires very small amount of energy, whereas nuclear state energy change requires a huge amount of energy. So they're very different. We are looking into how the nuclear states can be affected by the change in the electronic environment around your system. However, this change or this hyperfine interaction is pretty weak. So that is one of the problems. Second problem was that the recoil, because a gamma ray is a huge amount of energy, which actually creates a lot of motion around the nuclei, whether it is leaving gamma ray or it is absorbing gamma ray. So that's why this recoil energy actually creating a huge problem for the resonating condition. And that's why the resonance was not happening. And in general, we see a huge broadening of the line, which actually can come into effect and help us because it actually can create some space where there's a possibility of interaction. However, this is actually pretty small conditioning if you are creating a very free atom or very free molecule for doing a Mossberg. And this broadening is happening because of the Heisenberg uncertainty principle. Now, if we can create a solid lattice and make sure that molecule or my atom is not moving too much, it is only left with lattice vibration. And this lattice vibration, depending on the system, will happen at a very low level and it will not lose enough energy with this vibration. And we can have some condition where we can have almost recoil-less condition. And at those conditions, we can have a resonance and we can have a condition where we can see a transition from one nuclear state to the other nuclear state using very similar nuclei. And that is known as the Mossberg effect, where we can have this recoil-less condition. Any question or query up to here?
So my question is ER equals to 0 when it will be approached, like when n equals to 0. This
When
is the
n equals
condition
to
that we
0.
have got.
Yes.
Right.
So now think about, because this vibration also depend on temperature. So what temperature would you like to do your Mossberg spectroscopy? At high temperature or very low temperature? Think about Vasudha. Where would you like to do your Mossberg spectroscopy? High temperature or low temperature? Think about how temperature is connected to phonons.
Of course, low
So where the
temperature will be
increasing temperature,
Yes.
vibrations will be more.
Yes. So at high temperature, you have more vibration. So you are actually inducing, okay, go to the higher vibration or higher phonons or with n equal to higher number. But if you go to very low temperature, close to 4 Kelvin or close to liquid nitrogen temperature 77 Kelvin, over there, what happens? Not much temperature is there. So most of them will end up n equal to 0 or recoilless condition. So most of the Mossberg spectroscopy is done in the low temperature. Can we do that at high temperature? Yes, we can do that, but your resolution will be pretty weak. Okay, very broad spectrum will get.
Sir,
Has it
is
answered your
there
question?
any ideal recoilless? Ideal recoilless will be at absolute 0 Kelvin, na?
Yes, but actually we'll come into the next class. We don't really need to have an exactly recoilless system because we can use Doppler effect for our own good, because some recoil may happen and we can actually tune that for our own good, or I would say our own technology, to use it for our own benefit and use it such that we can actually have a transition even with a non-recoilless transitions. We'll come into that. But over here, I want to mention non-recoilless means very close to N0 transition. If you have N20 transition, that will not be possible, but say N0, N1, N2, N3. If that is happening, I can still tune that and have a very good transition. We'll come into that next class, how we can do that. Okay, any more question?
So when we will see the exact overlapping between these two bands of the source and the
Yes,
absorber.
yes, we'll come into that next class. I will give you few examples of like how different conditions I can change and how I can tune when the absorbance, this overlap will happen and how I can tune this overlap to get my actual Mossberg spectrum. We'll come into that next class. Any more questions? So you all